Okay, then yeah, so I can start. Thank you very much, Jana, for the introduction and also for the invitation to speak here. It's an honor for me to share you my opinions and results about deepfakes. And in the next 45 minutes, I want to give you some results and thoughts about the detection and the generation of deep fakes, and in particular also all the results that are part of a project, Fake ID, that we do also together with Jana. But before I start with the deepfake topic, I just want to say a few words about me. So Jana mentioned I have two affiliations. I'm heading a department, Vision and Imaging Technologies, at Fraunhofer HHI, which is a German national research organization. And I'm also professor for visual computing at Humboldt University in Berlin. And at both institutions, we are working on computer vision, on graphics, using methods of deep learning, and we have several applications where we apply these methods, and they are in the area of multimedia, industry, construction, medicine, but also on security. And I will focus in this talk about the security aspects, but the last slide, maybe as an overview, we are working on image analysis and synthesis. So basically all kinds of camera input is taken, and we try to understand what is in the image, in the video. And this can be information like geometry of objects. It can be information about what kind of objects are there, tracking information, motion deformation, deformation of 3D objects. And one particular object that we are interested in since a long time is actually the human. So we have a lot of activities in tracking human motion, in analyzing human bodies and faces. And this is also where the relation to the security applications come in, because faces or other information are often used as a means of identifying people. So we had a lot of activities since a long time about deepfake detection, morphing attacks, presentation attack detection, and all kind of analysis of humans and human faces. And having said that, as a short introduction about our activities, I want to focus a bit more on deepfakes. And you've certainly all seen many different deepfakes that have higher and higher quality. So it's basically some kind of thread to many different applications. So for images, maybe we are already used to the fact that if you see an image, we can think of that this has been photoshopped, it's been edited, and it might not be the true images. For videos, this is maybe a new experience, but now there are more and more videos popping up that that are fake videos or manipulated videos where the person you see is certainly not the original person in front of the cameras. And this is a threat to any to news, to politics, but also to security application where you want to identify person, like the video ident system. And in a deepfake, often you take an original video, so this is the original video, and then you just replace the identity. And in that way, you can make any person doing anything you want. And that's, of course, not very nice, and it can pose a lot of danger. So you also want to have tools to detect such deepfakes. And one threat is also that this is something which cannot only be done by secret services or with very high effort, but there are many tools available. So every one of us can easily create a deepfake attack. And so we will certainly see many deepfakes in our environment in the near future if you haven't spotted them already. So in this talk, I will focus a bit for the deepfakes on, on applications for face verification, where the identity of the person need to be verified, for instance, with some other security document like passport or security document. But there are also other potential attacks on face identities. For instance, if you want to modify your identity, you can also alter your own appearance, which is often called the presentation attack. So here you, you, for instance, you can wear a facial mask, you can alter your face with makeup and try to adopt another identity, or you can just show an image or anything in front of your face, just replacing the identity of your own. And there are, for instance, face morphing attacks, and this was something that was, maybe discovered in 2014 and has been around since then. And here, the idea of a face morphing attack is that if you have two different identities, then you have two different passport images, but you can basically create an in-between passport images, but by aligning the images and blending between them, and then you have some intermediate or in-between virtual identity. And it turned out that many face recognition systems actually allow then both identities or individuals to access a face recognition secured area, but by presenting this morphed faces. So these are different attacks, so I will not focus a lot on them, focusing more on the deepfake, but I mentioned them here because I will address them at some points to show different effects that are very similar to the analysis of deepfake attacks, and where we have also results that can be used in the deepfake detection analysis. And for the detection of these deepfakes, we are also involved in a research project. I mentioned that in the beginning, called Fake ID. This is a project funded by the German Federal Ministry of Research and Education, and there are many partners in there. So we have, for companies, we have the Bundesdruckerei, which is the German national company for printing passports, but also for identity management. We have the BioID, which is a smaller company specialized on detecting faked images and video material. And we have also research organization like the University of Magdeburg, where also Jana is involved in the project, and the University of Business and Law, who are mainly doing with the legal aspects. But we have also many associated partners from police and administrative and government organization, and also DHL as a provider for video ident systems. And within that project, we are developing different deepfake detectors. I will focus here on the deepfake detectors that we are working on at Fraunhofer HHI, but there are other deepfake detectors, for instance, from the University of Magdeburg, and we are building a pool of detectors which are then fused in order to come up with something where you have different means being investigated in order to judge if a image or a video is actually a deepfake or not. And within that project, we focus on a particular application. I mentioned at the beginning, the video ident application. And here, you certainly have also, maybe participated in such a video ident process, which is often the case when you open a bank account or something. So traditionally, at least in Germany, you had to go to the post office and tend to identify yourself. You want to set up a bank account. Now you can do that in an online chat, but if you have access to all the digital data, you could of course, just replace your own identity. So the camera captures you, you exchange the identity, and then you stream a video with someone else being shown to the person at the other end. So you can swap identities and maybe open accounts on a different name. So here you have certain restrictions, and of course you have maybe other opportunities by not only exchanging your own identity, but also the identity of your security document, for instance, a passport or identity card that you have to show into the camera and upload. So we are investigating all these aspects in the project. So we are looking also at the security document. This is the easier part because it's a more or less rigid object, but still it has some, security features on which make it more difficult to fool or fake such a system. But you could still exchange, for instance, the name or the passport image by if you have access to the digital data. But since we have also these security elements, like for instance a hologram, you have parts which change colors, you have flipping contrast or other information that appears and disappears even under an RGB camera image. You can use this kind of information to check whether a document is more genuine or might have artifacts or might be manipulated, or you can use this kind of information also to generate these deep fakes for training data of the detectors. And that's what we are doing in the project. But the more interesting case are deep fakes where you actually directly exchange the identity of yourself, and we're doing that mostly on face swap deepfakes. And there the idea is to take a real video sequence of a real person, for instance, the attacker, and then to track the face and only replace the inner facial part by the new identity. This might create deepfakes which are not fully identical to the new identity, since the hair and the background is basically copied from another person. But if they are similar, this might not be detected. And in particular for the video ident scenario, usually it's a blind scenario, so the person doesn't know the other identity at the other end of the communication channel. So, and on the other hand, you avoid creating synthetic parts of the hair, which is often difficult to create realistically and consistently. And often there are artifacts that you can spot, and by avoiding the synthesis of hairs, you can reduce the artifacts. On the other hand, you have maybe other artifacts like blending artifacts or other different statistics, because the outer part and the inner part may come from different sources. And if you want to detect deep fakes, it's not an easy problem. So what you or the goal is to distinguish two classes of images or video sequences. So you have real video sequences taken of a camera of a real person, and then you have another class of images where you have a video sequence taken but manipulated afterwards. And the problem with that is that on one hand you have a lot of in-class variations. So you have different identities that you have to address. You have to deal with all kind of illumination, environments, backgrounds, facial expressions, appearance. Images are taken from different cameras, laptops, mobile phones, and so on. So statistics can vary a lot. And on the other hand, you have to detect small details in the videos. And with all the progress in deep learning and also in deepfake generation, the quality of the deepfakes get better and better. And therefore it's more and more challenging also to detect this artifact. And this is something like a rat race where detectors and attackers maybe run in parallel for a long time. But if you want to distinguish them, we have some different kind of information that we can use to detect them. And for instance, one very prominent one is any kind of artifacts that arise during the creation of the artifact. So if you blend something, you have blending artifact at the borders, you have blurring effect because maybe the deepfakes are not that that detailed. You can dive into sensor noise patterns, check image statistic, and look if the parts are consistent over the spatial time, but also temporal time. Temporal inconsistencies is something very worth looking at. So for instance, is the appearance consistent over time? Is the geometry in one frame the same as at the end of the sequence, depending on pose, on motion? So there are many temporal effects, and usually the deepfakes are often created, at least to some extent, frame by frame, so there could be differences in between. And we can also look at semantic inconsistencies, looking, for instance, at the eye blinking rate, which could be non-real because these deepfakes might create less eye blinking. The illumination might not fit in the inner part to the outer part, and more things. And yeah, given all these kind of effects, we can now train or create detectors that are able to detect such kind of deepfakes. And here, a very simple experiment that we did. So we trained a simple neural network. It's just a standard classification network, VGGA, and we trained them on different deepfake data sets, the celeb deepfake and deeper forensics. And then frame for frame, we basically tried to find out if this is a deep fake or not. And if you look at the results, they are astonishingly high. And this is also due to the fact that these deep learning methods have a high power of distinguishing small effects. But even if you use other data sets, you get a rather high accuracy and result. The question is basically now, what do we do with all these accounts? So we could say if we have detection rates of above 90%, we're safe. So we can detect all different deepfakes, at least with high probability. But on the other hand, the question is, so what do we do if the detector says, yeah, that this might be a deepfake? And here you see we have only rates of 80%. So in 20%, the detector might be wrong. And if you want to reject all account openings at the bank, for 20% of the people, this might not be the best solution. So we need some kind of insight, what is actually happening here, and maybe to give a user the information why this is actually a deep fake. And this is not that easy because all these neural networks are typically black box systems. You feed in some data, you get a result out, but you have no clue on why the network has actually decided for a certain outcome or class. And here we can have different kind of modifications to our systems in order to get at least some insights for the detection results. So first, we can get back a bit, and instead of using some black box deep learning system, we could use some handcrafted features that are interpretable by a human being, so we get some information. And maybe we can also design the classifier that we can basically track back the decision. We can still stay at the neural network level, but add components that have a semantic meaning. And we do that, for instance, by placing differential renderers in between that synthesize something. So we have, at some point in the neural network, something that we can interpret as a human being. And then we can at least say, this might be okay, or this is completely rubbish. So semantics could be built in, or we basically look at semantic information. I mentioned, for instance, the eye blinking rate, which has been used for deepfake detection. Another information is consistency of geometry through poses if you turn your head. This has been addressed. And I will just show as an example also the blood flow analysis. And this is something, if you look at the human, at a live human, usually you have some heart rate and blood is throwing through your face and skin area. And you certainly know the system. You can use photoplethysmography in order to detect your heart rate, your pulse rate. And this is due to the fact that for each heart rate, you get a higher blood flow through your vessels. And this has a change in intensity. And from that, you can detect also pulse rate. And we have used that further in order to influence also to determine the actual blood flow as a temporal and spatially visible information. And we have used that also for other security applications here, for instance, for presentation attack detection. You have a video of a person showing some blood flow. You can detect the blood flow. It's all available in the face. But if you, for instance, put on a facial mask, a partial mask, then this mask occludes the skin. So the blood flow is no longer detected. And this could be a hint that you can interpret that there is something wrong and that there might be a mask. And we thought of that's nice information and use that also for deepfake detection, because if the deepfake is done frame by frame, you miss maybe these temporal effects. So this is an original video. We can determine the heart rate. It's around 70 beats per minute, and everything is fine. So we run the same method on a deepfake. So now we have another heart rate, but the astonishing thing was that we actually could detect a heart rate. And at least our interpretation of that is that the driving video of the person has a heart rate. And even if we do a frame by frame synthesis of heart rates, then we basically take over the heart rate of the driving sequence and then have something, a deepfake that has also a heart rate as shown. So we cannot use that kind of information. But if you look at the blood flow, typically for the original videos, you have a blood flow from the top to the bottom where the arteries basically insert the blood to the top and it's going down. But for the deepfakes, we have some strange wobbling effect, and it has no physical meaning anymore. And currently, we're investigating that property also for a larger data set. And for the original videos, we have all the nice blood flow, but for the deepfakes, we have these strange artifacts in there where we are currently building detectors to find that as a semantically interpretable information. The other direction that we can take to get some more insight is that we use explainable AI. And here we have been using also layer-wise relevance propagation, which is just one method that has also been developed here at Fraunhofer HHI to get some information about deepfake decision. So here, if you have, for instance, an image, you want to classify that. If there's a castle in there, you run your network. It says, oh yeah, we have a castle. And now you invert the process. You go back from back to forth, and you propagate relevance through all the layers, and you end up with a heat map. And here the red parts show the important part, which act as for castle, blues are against castle. And here you can see the castle is highlighted in red. So the classifier has maybe learned the right thing. This might not be always the case. Here are two examples from a colleague of mine. So for image classification, and they found out for a popular classifier that for some classes, the classifier turns out the right result, but because of the wrong reason. And for instance, for classifying horses, the detector looked at the logo and copyright in the lower left, because all the images of horses had the copyright tag in there. So, and this is something where a deepfake detector can provide the right result, but it has completely failed because he hasn't looked at the image. So you cannot trust here the result. And that's something we can also exploit here in the analysis of our deepfake detector. Here an example for presentation attack detection, where we want to classify, for instance, a display in front of a face by looking at the geometry. You run a simple classifier. It always provides, or in less than or 1% of failure cases, so it's mostly true, it provides the right answer. But when looking at the at the LRP results, we see that the detector basically looks at the outline, and the display has a different outline than a person. And of course, you can distinguish things, but it might not be the right result, because if you take a picture, you cut out the person and then present it in front of a camera, yeah, everything is fine again. So you can use that to modify your algorithm. We did that, and now the classifier performs well. And for instance, if you have some fingers in the face, it's clearly highlighted as against true face. If you have a bent piece of paper, yeah, you have some region that seem okay, but many parts are no face, and for a flat region, everything is remarked as as a wrong, and not being a real face. So now we have a detector that is performing similar well, but because of the right reasons. We did similar things for the face morphing detection, and here we found out similar things. The face morphing detector looked only at the eye region, and that's maybe plausible, because most artifacts occur in the eye region, which are high frequent. But the detector does ignore all the other areas. So if you just don't fake the eyes, everything is fine again. So again, you can modify your detector and create something, for instance, by cutting out some region. You enforce the network to look at other region, and suddenly, if you look at the results, you look at more structures in the face to detect whether a face is manipulated or not. And the question now is this method usable also for non-technical people? And here we use that in order to improve our detectors. For that, it works fine, but other people who want to inspect maybe an image and say if this is a genuine or a fake image, you need some more direct information, and these LRP results sometimes turned out wrong information. So we extended that version as a focus layer-wise relevance propagation. And this is a somewhat similar tool, but it only looks at the convolutional part of a detector and has thus a much better localization of artifacts in the image. So you can basically directly show in the image where the artifact is. And for most of the results, these extensions show similar results to the original explainable AI technique. So you see all the information highlighted, which needs some further inspections. But in case of maybe the detector has misclassified the results or is very unsure, then this LRP can basically show something completely wrong, for instance, highlighting the wrong eye. So here, the right eye here, this one has been blended, or there are artifacts in there. This one is okay, but you show the wrong eye. And with that, you can basically detect areas and show, look at these areas. They are very, they are potentially faked, and you have to look at them. And that's something you can also do at the deepfakes. And for the deepfakes, we have similar results. We can train our detector on deepfakes and real images, and then if we get a decision, we can feed that back and get some information on why the detector actually thinks of that this is a deepfake. And what we found out for all these, yeah, official research deepfakes, that detectors, they basically look at the eye region because there are some obvious artifacts in there, and this is sufficient to detect if there's an artifact in there. But ignoring all the other thing is not something that is very robust, so you have to um, yeah address that in the development of the detector to look also at other regions, and I showed some potential ways of how to do that. The other problem that we focused is that if you look at these typical data sets that are usually done for deepfake classification, they have a lot of artifacts in there. They are automatically generated to generate large content, and they have many things where the human immediately sees that there's something wrong here. For instance, the eye is closed, this is open. We have here wrinkles that are asymmetric and popping up and down. This looks very cartoonish. Here there's an earring which changes depending on when you see the ear. So there are different earrings. So there are a lot of artifacts in there, and it's very easy for simple detectors to spot these artifacts, and then they are no longer able to detect the more severe effects. So we worked also on improving deepfakes in order to create high quality data that we can use in our deepfake training of the detectors. So we started with simple versions with these dual autoencoder types, where you have one common encoder for different identities, but you have individual decoders that can synthesize the images. And then if you replace the decoders, you can input one driving image and synthesize a new identity. And the goal or the idea is that the latent representation, because it's done over all identities, extracts all the information that is less affected by identity, but more on facial expression. We have somehow, since we are doing that only for the facial region, we have a synthesis of the inner part of the fakes. So we have now with the mask, to feed that back into the driving video to get our face swap deep fake. And if we do that, so we also figured out some problems because the faces do not they have different geometry, so they might not align on a pixel level, which leads to artifacts, for instance, flickering artifacts at the borders or at hair areas. So we extended that our synthesis part to synthesize also facial mask for the synthetic part. Then we XOR all the mask in order to have only valid regions that are blended. And now we have something where we can replace identities, and I hope that you can see that this person is replaced. It's another identity, but it shows very high quality, and it's very difficult to spot any artifacts in there in the video. And this is also true for other sequences, which are a bit more challenging. They might not be typical for video ident videos, but even here with a lot of head pose movements, there are quite some good results and little artifacts in there. So here you see a head turning, but still the results are a bit blurry. So, but now we have all these nice diffusion techniques around that you all know from DALL-E or Stable Diffusion to generate high quality detailed images. So we also use diffusion techniques to create first low resolution deepfake with our autoencoder and then upsample that to very high resolution images. And if you look at them, now we can create deepfakes that have a much higher resolution. I'm not sure if you can see that, but if you zoom in our original autoencoder, we get a certain eye with some blurry results, but here eyelashes are showing up and you have much sharper content just by having diffusion techniques that synthesize the images instead of a GAN or an autoencoder. And this provides us then with deepfake data that has a very high quality and where it is much more difficult for a detector to find out where the artifacts in there. And this is something we tested also on a very simple or on a more enhanced deepfake detector, how much influence actually the data set for training has. So we used detector, the real forensic detector from Haliassos from 2022. And this is a very nice approach, which not only uses video information, but also audio information. There's some student-teacher training, and the student has always to predict from video the audio properties and from audio the video properties. And by doing that, you force the detector to learn also temporal information, because the audio information is mostly temporal, so there's no spatial thing from the video sequence, and you get a detector that is very robust and looks at consistent things over time, and it generalizes very well in contrast to other detectors. And we use that detector as a base and tried it with different data sets. So first we used the face forensics data set, which is a typical data set used for evaluating deepfake detectors. And here, these are results taken from their paper. So you have basically very high recognition rate. So deepfakes are detected almost 100%. And even if you train your detector on face forensics, if you test them on other data sets like celebrity deepfakes or the deepfake detection challenge data set, you have still very high results in detection. So now we took this same detector, we trained it on face forensics, but then tested them on our own data. And if you do that on the real data, we still have the same quality. But actually, if we now provide our own deepfakes to the detector, it basically breaks down. And if we average, or if we have here some in-between balance, we are close to the 50-50 chance of detection of real or fake image. So this detector does not work anymore. But if we now fine-tune on these enhanced deepfakes, and just by using a couple of them, we can drastically increase the rate for detection of those deepfakes. Of course, they are now also, at least to some parts, also in the original training data. But we now have a detector that detects the new deepfakes very well, but it can still detect all other databases with very high accuracy. And this means that having the right training data set is essential for creating a deepfake detector, although you also need clever detection or detector algorithms and architectures in order to extract the right information. But having a broad database with different kind of deepfakes makes it more difficult for new attackers to find some hole in the high-dimensional feature space that is not addressed, and which makes it difficult to have a robust situation. So so we use that as a starting point, also to continue with improvement of deep fakes. So we are now also looking at really 3D deep fakes, where we use 3D models as an underlying representation in order to get, for instance, pose consistencies much better. So this is just some kind of learned neural graphic system. So you have at the end a mesh that you can animate, you can control it, you can change it, and fake the identity by by basically learning geometry and images from a video sequence. Of course, here you need a full video sequences as a target identity. So a single image is no longer sufficient. But if you have a sequence available, you can now train geometry and textures, and then you have a CG model that you can animate. And of course, the CG model, it looks, of course, very coarse, and you can immediately spot that this is not a right face. But you can now use deep fake generation techniques, 2D techniques that just improve the rendered 3D images. And we synthesize some correction images, and we end up with something at the end which looks very natural and has still the underlying 3D representation, the semantic representation. So we can change blink rate, we can change expressions, emotions, but still create something that looks realistically. We get an alpha mask as a side product, so we can blend in the person also in other video content and to create something which is completely fake. And yeah, this works quite nicely. So this is the result, for instance, of a person that where we only have one video sequence available, no information about the person. So this is a public data set that we used, and we can still synthesize everything together with all these reflections in the glasses and the teeth and so on. So this might also create new opportunities and dangers for deep fakes. And with that, I also come to the end of my talk. So I hope that I have shown you that deepfakes are a threat, that you can create now videos that are very difficult to distinguish between between real videos. So you cannot trust anymore a video that this is really a genuine thing that had happened in reality, but you have somehow to check whether a video is actually a real video or a fake. And it's not an easy problem because deepfakes are getting better and better. So you have to find all these inconsistencies in the video because it's actually a blind classification problem. In my opinion, there are a lot of chances still around in the temporal domain, consistencies across all different domain and low-level statistics, but also on semantic levels can still be exploited. But of course, if you have a detector that can detect something is wrong, you can build your deepfake generator that uses that detector in order to improve also the deepfake generator. So it's still a problem. You have somehow to address interpretability and explainability in order to basically use the decision of a detector. Because if you just get black box decisions, you cannot basically decide anything on these decisions because you never get 100% questions. So you need somehow to address that problem, that you provide information to the user why a video is a fake or not. And yeah, I mentioned that we will see certainly higher quality fakes, but also the detectors will improve, and this will certainly go along for a long while that the detectors and attackers will fight against each others. And yeah, it's difficult to say who will win at the end, but maybe we come to some place where we reach something where detection is something which works well enough to handle all the practical application around. And with that, I would like to thank you for your attention, and I'm happy to answer questions if there are anyone. Thank you very much.